This is Mr. Anderson for Kellogg Community College. We are going to go through part 4 today of the test review, and we're going to take a look at how we can use dice charts and how we can find the probabilities of rolling dice and drawing cards, and we'll investigate deeper into Venn diagrams, the idea of the term complement, and also look at scientific notation for incredibly small results. Now, what I would suggest you do is on the day of the test, at the top of your paper, is make a dice chart. A dice chart shows the sum, and I'll use sigma to use that, the sum of rolling two dice. And this is going to be like the game craps, or any game where you would roll two dice like in Monopoly. So this is a sum of the first die being 1 through 6 and the second die being 1 through 6. And I will show you how quick it is to make this. So you'll just make some vertical lines here to separate each of your values and horizontal lines to do the same. So this gives you something called a sample space. And the sample space creates all the different possibilities of a certain event. And in this case, rolling two dice, the number of possibilities is 36, because 6 times 6, these two independent events, make a total of 36. So 1 and 1 make 2, 1 and 3, or 1 and 2 make 3, 1 and 3 make 4, so 5, 6, 7, and then 2, 3, 4, 5, 6, 7, 8, because like 2 and 6 make a total of 8. And you can see how the chart easily kind of is made, and it's quickly made. And if you are not explaining it as I am to someone in the room while you take the test, creating the dice chart of the sums of these dice is incredibly easy. Now, what you'll note, though, is that this is getting a little messy because I'm trying to write with a light pen, and that's really just due to my poor handwriting than anything else. So what I've done is I have actually created a dice chart here, so I can kind of use this as a static symbol here, and I can draw on this as well. So let's take a look here. I'm going to go back to my drawing pen, and now let's write this. Now, I will have to say that on the day of the test, you can choose one of two options. You can either use a reduced fraction. Oops, I should change the color there. You can use either a reduced fraction, or a percent to the nearest tenth. So round to the tenth. And rounding to the tenth would mean that the percent would be like, for example here, an example of a reduced fraction would be like 1/4 instead of 13 over 52, which is basically picking a club out of a deck of cards. And a percentage rounded to the nearest tenth would be like 16.7%. The tenth is 1 decimal place after the decimal. So let's now start over by changing my color to something a little bit more legible. Alright, there we go. Go back to blue. Alright, and let's now reset this. So get everything kind of ready to go for these problems. Okay, so the probability of a sum of 7. Now what I'm going to do is take a look at how many different 7s I have on the dice chart. I have 1, 2, 3, 4, 5, 6. I have 6 7s on the dice chart, so the answer is 6 out of 36. Now, if I was to reduce that, I can divide top and bottom by 6, which makes 136. And if I divide that on the calculator, it's 16.6 repeating, or 16.7 rounded correctly. The probability of a sum of 2, well, there's only 1 2 here on the chart. So that means the odds are 1 out of 36, or the percent chance of, and that's completely reduced because you can't reduce it any further, or 2.8%. Now remember, on the test you can choose either whether you want to use fractions or percent rounded to the nearest tenth. My suggestion is stick with one of them. Don't write both down, because in case you get one of them wrong, I'm not sure which one you want me to count. So please choose one or the other, but don't choose both. Circle your answer too if you want, if you've written down both, circle the one that you want me to look at. The probability of even sums, like how many of these are even? Well, I'm going to circle all the even numbers on this chart with the even sums, and you can see that I'm going to be circling 3 in each of these rows out of 6. Well, if I'm circling 3 out of 6 in each of these rows, then the odds are going to be 50%. But if you counted up the circles here, that would be 18 out of 36, which is reducible to 1/2 or 50%. You'll note that I don't write 50.0%. Now let me clear this off here and move on to the next part. That way we can kind of keep going here. There we go. Let's get the pick back. Boop. All right, so now we're on to the next three. The probability of sum of 11. Okay, so the sum of 11, it looks like I've got 2 of those right there, and I'm not going to mark that up right now. 2 of those 11s, so the sum of 11 is going to be 2 out of 36, which the top and bottom of this fraction can be divided by 2, so 1/18. And if you were to divide that on a calculator, it rounds to 5.6%. The rounding rule has to be applied. 5 and above, give it a shove, so make sure that this is rounded correct. Now this one always causes a little bit of stress. It's having at least 1 3. That means if I roll a die and I have at least 1 3 in it, I have to count it. Now the easy one to see is this double 6, or this double 3 to make 6. But also this one, and all of these have at least 1 3 in it. Even though the 6 had 2 3s in it, having at least 1 3 is met by that criteria. Also, these examples also have at least 1 3. So you'll notice that 3 6 has 1 3 in it, and same with 6 3 has 1 3 in it. So if I count up all the circles, 1 2 3 4 5 6 7 8 9 10 11, I have 11 out of 36. But this brings up a very interesting point. I would not double count the 6. I would count only the number circled, because 6, which is made by 3 and 3, can only be made one way, and that right there means we will not double count it. If I reduce that to a percentage, it'd be 30.1%. Now the probability of rolling doubles, you saw me start with this 6. I'm going to fill this in now. If I start with that 6, you'll notice that this is a double as well. This is a double as well. This is a double as well. So this diagonal here represents all the doubles that can occur when you roll 2 dice. So, 1 1, 2 2, 3 3, 4 4, 5 5, 6 6. So the probability of rolling doubles is 6 out of 36, just like rolling a sum of 7, which we've done in an earlier problem, which is 1 out of 36, or 16.7%. Okay, let's reset the screen again, and let's move everything down just a little bit, because we're now going to look at the probability of sum of 7 or 11, and we're going to get to the Venn diagram in this case. So let me see here. Yeah, let's move this here. Okay, the probability of rolling a sum of 7 or 11. Now, you'll notice that the probability of rolling a sum of 7 in a previous problem was 6 out of 36. I'm going to write the unreduced fraction here. The probability of rolling a sum of 11 is 2 out of 36. So the probability of rolling a 7 or an 11 is going to be 8 out of 36. And I knew that before looking at the chart because these are mutually exclusive events. These events do not overlap or interact with each other. Because rolling a sum of 7 is these 6 possibilities. Notice that I'm going to circle them. Rolling a sum of 7 is 2 out of 36, so there's 2 of those. And there's no overlap or interaction. So 8 out of 36 would be this situation here. And we can reduce that by dividing top and bottom by 4 to make 2/9, or 22.2%. And another word about rounding. This is if you look at a decimal of this, it's 0.2 repeating. But 2 is not bigger than, 2 is below 5, so we do not round that to 22.3, even though it never terminates. So now we're going to look at doubles or a sum of 5. Now, we looked at the doubles before, and I'm going to use squares to represent this. These squares represent all the doubles, so you'll notice that the squares are going in that diagonal. So there are 6 doubles. So I'm going to just put a little 6 to kind of keep track here. And a sum of 5 are these squares. So these 4 squares here, and that means we have these 4. Well, there's absolutely right now no overlap there, so there are 6 doubles, a sum of 5, there are 4 of them, for a total of 10 over 36, and that 10 over 36 can be reducible. If you take the top and bottom and divide it by 2, you get 5 over 18, which is 27.8%. On some of my paper answer keys, I might have had that as an 11, so I'm sorry if that was there on some of your paper answer keys, but it really should be 10. Now let's look at doubles or a sum of 6. Now what we just did is some mutually exclusive events, but this next example here with dice is not mutually exclusive at all. Which means that if we look at the probability of rolling doubles, and let's now go back and circle those doubles, so 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So here's our probability of rolling doubles. Now let's look at the sum of 6. This is the 1 and 5, the 2 and 4, the 3 and 3, the 4 and 2, and the 5 and 1. You'll notice we do have an overlap, and that overlap is right here. That's the overlap because the probability of rolling doubles was 1, 2, 3, 4, 5, 6. There were 6 of them. Rolling a sum of 6 is 1, 2, 3, 4, 5, but we also have to subtract the 1 overlap. And the overlap in the book has been taught by the union of sets A and B. So if this is the set A of doubles and this is the set B of the sum of 6, then the A union B, or sorry, A intersection B, I was saying union the last couple times, the intersection of A and B is that overlap that we have to not count twice. Now, so if you're a dot counter, which I would suggest because it's easier to do, you would count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So like the previous problem, which was 10 out of 36, reducible to 5/18, and reducible to the, or sorry, changeable to the percentage of 27.8%, you would be easily countable to do that way, even if you never learned the A, B, adding the A and the B and subtracting the overlap. Now what I want to show you is the Venn diagram, and the Venn diagram, wow, those are good circles, not. The Venn diagram is going to be looking at the probability of rolling doubles. That's P of doubles, so the probability of doubles, and P of the, well, P of the sum of 6. I'll use the sigma to simplify that. And now what I'm going to do is set up all the possibilities of rolling doubles in the sum of 6, but in the intersection here, that A intersect B, this little wedge here, I'm going to put where the two groups collide. So 1 and 1 is a double that only occurs in the doubles category. 2 and 2, 4 and 4, 5 and 5, 6 and 6. These are all the doubles I can get. Now, you'll say, but aren't you missing something? It's like, yeah, I am missing something, but you're going to see where that comes in just a second. Now let's look at the sum of 6. This is going to be 1 and 5. This is going to be 5 and 1. This is going to be 2 and 4, and 4 and 2. But you're saying, but Mr. Anderson, what about 3, 3? Well, that goes in the middle here, and I made it way too small to kind of put it there. But yeah, that would be where it went. It would go in 5, it would go right there in that little gap, 3, 3. And that would draw the Venn diagram. Because the Venn diagram has these elements that are doubles, these elements that are ways to get 6 by adding up the dice, and then the shared element of these two sets is 3, 3, which is not only doubles, but it also is a sum of 6. So for our next set of problems, we're going to look at cards. And it's helpful to remember that there are 52 cards in a normal deck of cards. Let me see here. And we're going to look at these specific problems, and there won't really be a reason to list out all 52 cards, so there's no card chart. These will be much more straightforward. Now, again, we'll use fractions or percents rounded to the nearest tenth. So the first thing we're going to do is look at the probability of getting an ace. Now, there are 4 aces in every normal 52 card deck of cards, and that would be simplifiable to 1/13. Now, you can also change this into a percentage by dividing the two, and this would round to 7.7%. A club in the deck of cards, if you look at all of the clubs from 2 through ace or ace through king, there are 13 clubs in a normal 52 card deck, and that would be 1/4 of the deck, or 25%. And again, as before, we don't write 25.0%. Now, getting the ace of clubs, now there's only one card marked ace of clubs, so there's only 1 out of 52 cards that match that criteria, grabbing that. And that right there is going to be 1.9% if you divided the two. Now, the complement of P, which means the not getting the ace of clubs, is going to be 51 over 52. So let's talk about complement. The complement of an event is not getting that event. So E bar is the symbol that we use for complement. So if my probability of the event is 1 out of 52, then my probability of the complement, which is 51 over 52, or probability of E bar, is going to be equal to 1. The probability and its complement will always equal to 1, or 100%, which means that I can rewrite this like so. I can go 1 minus the probability of the event will give me the probability of the complement. So, as I showed here, if this is the odds of me getting an ace of clubs, here's the odds of me not getting the ace of clubs, or 51 over 52. Percent-wise, that would be 98.1%. The probability of getting a heart or an ace. Now, here's where things get a little bit tricky here, because a heart, there are 13 hearts in the deck of cards, and there are 4 aces in the deck of cards. But there is an overlap, though. So this is a true application of the probability of A, getting a heart, probability of B, getting an ace, but then you have to subtract the overlap to get that event right there, because the overlap is the one card, the overlap, which is the ace of hearts. So 13 plus 4 minus 1 is like 13 plus 3, or 16 over 52. 16 over 52 is reducible to 4/13 if you're going to write the fraction of that, and 30.8% for the percentage, rounded to the nearest tenth. Getting a 3 of clubs or diamond, the 3 of clubs, well, there's only one 3 of clubs, and diamonds, there are 13 of them. So getting a 3 of clubs or diamond, notice there is no overlap. A 3 of club is not a red diamond card, so this will give you a total of 14 over 52. And 14 over 52 is reducible, dividing top and bottom by 2, to 7 over 26, which is 26.9%. Getting a heart, or an ace, or a 9. Now for this problem, you have to think about these types of cards, but now really concentrate on the overlap. The probability of getting a heart, there are 13 hearts in a deck of cards, as we talked about like up here in getting a club. Now an ace, there are 4 aces in the deck of cards, as we talked about here with getting an ace. Now getting a 9, there are 4 nines in the deck of cards. But what you have to consider is that if you count all 13 hearts, you are counting an ace and a 9 of hearts. So your overlap in this case, or your intersection of A, B, and C here, is going to be 2. Because in thinking of your hearts, you're going to be already counting one of the ace of hearts and one of the 9 of hearts. So your overlap is 2. So it's 13 plus 4 plus 4 minus 2, or 13 plus 4 plus 2, and that's going to be a total of 19 over 52. That fraction isn't reducible, and the percentage is 36.5%. All right. Now we're going to move on to our final part here. The most challenging part of all the card problems is dealing with the, the most challenging part of all these problems is that we're going to be given A and B, which means that these events are going to be multiplied by each other, which has the chance of making some very, very small numbers. So in our first example, the probability of A is getting tails on a coin, and the probability of B is rolling 3 on 1 die. So in this part of the test, it will probably say percents only. So even though we will be setting the problem up with fractions, this part of the test will say at the bottom of that page, page 5 probably, percents only. Or page 4. I don't forget which page it is. But I will tell you that we need percents because I want you to not get around having to know scientific notation for very small percentages. So getting tails on a coin, probability of A is 1 over 2. The probability of rolling a 3 on 1 die is not 3 out of 6, it's 1 out of 6 because we're not asking for 3 out of 6 possibilities. We're asking for that one possibility. We're rolling a 3 on 1 die is 1 out of the 6 faces. Now multiplying fractions, not a problem. Top times top, bottom times bottom, and this makes 1/12. 1/12 is the answer to this problem, And we can now, because of the percents only description, we divide on our calculator 1 divided by 12 and get 8.3%. The next piece is drawing a queen. So the odds of drawing a queen are 4 out of 52. And then we're going to replace that card back into the deck and draw a diamond. Now, since we're replacing the card, we're still talking about 52 cards, and then drawing the diamond is going to be 13. If we multiply top times top and bottom times bottom, we get an answer of 52 divided by 2,704. Now, this we need to divide because this is a percents only problem, and we're given 1.9% rounded correctly. Now, here's where we're going to start to have some fun, getting 2 jacks in a row, and do not replace any card. So your first event is going to be drawing the first jack. So that's 4 jacks out of a 52 card deck. The next event is going to be drawing another jack, and that's going to be only 3 available in the deck out of 51 cards because you have taken one of the cards out of the deck. Getting 2 jacks in a row without replacement means that your denominator is going to morph or change. And this is going to give you 12 over the total of 2,652, and then we've got to divide these two. And this gives us a decimal of 0.005. Now, what you have to be worried about that is the decimal of 0.005 is going to be not the percentage. The percentage is bringing that decimal 2 spaces over, so 0.5% is the answer to that problem. And now what I'm going to spend the most time on is this last problem of getting a 7, 8, or 9 in order. Do not replace any card. So there are 4 7s in this deck of 52 cards. There are 4 8s in 51 cards and 4 9s in 50 cards, which gives us a fraction of 64 over 132,600. Now, this answer asks for percents only, so I need to present it in this way. And what I want to do is drag the calculator over and type these 3 fractions in and show you what happens. If you do this, and I'll bring my calculator over and show you what happens when I type this in. If I type in my 4 over 52 multiplied by my 4 over 51 multiplied by my 4 over 50, you now get the answer of, what the heck? See, this is a scientific notation. And the scientific notation for these fractions, I want to translate this for you because I cannot give you full credit on the test if you write down 4.8e negative 4. It shows a lack of understanding of what scientific notation is. But I want to convert this for you to show you what this means. The 4.8, and I'm not going to write the other numbers out, 4.8 e negative 4 is saying this is 4.8 times 10 to the negative 4th power. I really wish maybe some of these calculators would do that, would show you that it's 4.8 times 10 to the negative 4th, times 10, instead of using the e symbol. But I digress. What we now need to do is turn this into a decimal so we can turn it back into a fraction. Now, the negative 4 means we would move the decimal 4 spaces to the left, and here would be one of my 4 spaces. 1, 2, 3, and 4. So the decimal is going to be moved out here, which means I need 3 zeros in front of it. 1, 2, 3, 4, 8. So 1, 2, 3 zeros because I moved the decimal 4 spaces. Now what this is my decimal answer. My percentage answer is going to be moving this back 2 spaces because percentages, as I showed in the previous problem, are always moving back 2 spaces. This would be 0.048%. And the book might have it written this way because they would always go to the first non-zero number if the percentage is rounded beyond the 10th. So yeah, you do have to know your scientific notation for this test, and that's when you get a problem in this section here that's going to give you exponential notation, or the e negative number. So again, as a reminder, you would move the decimal 4 spaces to the left, so that means one of those zeros would be taken up by that, and you'd have 1, 2, 3 zeros and a dot right there, and that would be 0.00048 or 0.0005 or 0.05%, which is what I need for the final answer. Well, thank you for watching this other lengthy video to your test review. I hope this has helped, and I wish you luck on the test coming up. Thank you.